Welcome. In this lecture in linear data analysis, which has multiple sessions, we'll explore how we can analyze data by using graph methods. The main concepts for this lecture are we're going to revisit the Laplacian matrix of a graph and we'll re-explore the eigenvectors. We'll call this spectral clustering, and that'll be a way that we can find clusters within these graphs. We'll understand that the gram matrix, which comes from a kernel method, is quite closely related to some of these graph methods. One problem that we can keep in mind as we go through this lecture is how could we find more than two clusters in a graph? Let's recall some of our graph matrices. A graph is an object in discrete mathematics, and it's a set of vertices and edges. And we'll suppose that there are n such vertices, and from these we can form a square binary matrix that's symmetric, and this is the adjacency matrix. We'll say that no vertex can be connected to itself, so entry II is 0. And what we'll say is that entry ij of this matrix is a 1 if and only if vertex I and vertex j are connected by an edge, and otherwise it's the adjacency matrix entry is 0. We then form a degree matrix, and the degree matrix is the number of vertices that a given vertex is connected to, and that is either the row sum or the column sum of the adjacency matrix. And we'll then form a diagonal matrix by putting each of these degrees onto the corresponding diagonal entry. The Laplacian matrix, which is sometimes written as L, we'll keep the symbol K, is the difference between the degree matrix and the adjacency matrix. And we'll keep the symbol K because now we understand that this Laplacian matrix is a symmetric positive semi-definite matrix. When we explored binary clustering, we used the Fiedler vector. We now understand that because the Laplacian matrix is symmetric positive semi-definite, it's guaranteed to have a spectral decomposition as the orthonormal basis, which are the eigenvectors, then the eigenvalues are a diagonal entry, and then we just transpose that eigenvector matrix. We can order these eigenvalues. We can reorder if they come out of a computation in a different order, so that the first one is the largest and the last one is the smallest. We know, by the way that we constructed the Laplacian matrix, that if we multiply it by the ones vector, we get 0 vector. That implies that this smallest eigenvalue is 0, and the corresponding eigenvector is a multiple of the ones vector. Now, because these are an orthonormal basis, what that means is that if we take any j that is not equal to n, if we take any other eigenvector and we take the dot product with that last eigenvector, we must get 0. That's because it's an orthonormal basis. The Fiedler vector is specifically the second smallest, and because of this property, it has to be orthogonal to the ones vector, and if we take the dot product of this with a ones vector, that's basically adding all of the entries of this, and so every other eigenvector has to be a zero mean vector, and the Fiedler vector in particular will give us a binary clustering of that original graph. Let's just remind ourselves of one example. So here I have 20 vertices, and these have if we were to plot it in a 4x5 Cartesian grid, this is the graph that we would get. When we do this graph analysis, that is, we form the adjacency matrix, the degree matrix, the Laplacian matrix, we do the spectral decomposition, and we take that Fiedler vector. If we use the pluses and minuses in the Fiedler vector, then this is the sort of clustering that we get. So now, our question will be, how could we use graph methods to find more than two of these clusters?